Hey, we recently saw how to construct what we called the Maclaurin series, which is a power series centered at 0 for an infinitely differentiable function f. Now we're going to look at how to generalize that into something that we'll call the Taylor series, which is very similar to the Maclaurin series, except that it doesn't have to be centered at 0. And before we jump right in, let's see why we need such a thing. Take the function f of x is the natural log of x. And f of 0 is undefined for this function, so we can't even get started in our construction of a Maclaurin series because f of 0 is that first term c0. And if we tried to proceed anyway, we would find that the first derivative is also undefined at 0, and so is the second derivative and the third derivative, etc. And so if the natural log of x has a power series, it doesn't have one centered at 0. Okay, suppose we have an infinitely differentiable function f with a power series centered at a. Then that power series is f of x is equal to c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and on like that forever. How do I know? Because every power series centered at a looks like that. The only difference between them is what are the constants c0, c1, c2, c3, etc. So our goal will be to figure out what those constants are. If we can do that, then we will have found the power series. When we were doing this for Maclaurin series, we very cleverly found c0 by plugging in x equals 0 and seeing that all the terms except for c0 went away. Well, we can't do that with 0 for this power series, but we can do that with a. If we try to compute f of a, it's c0 plus c1 times a minus a. Well, a minus a is 0, and then we get c2 times a minus a squared, that's 0 squared, and every one of the remaining terms has an a minus a, which is 0, as a factor, and so they all go away, and we get that f of a is equal to c0. Or, more interestingly, c0 is f of a. And then just like we did when we were developing the Maclaurin series, we can take the derivative and evaluate it at a, and we see the same thing happens. All of the terms aside from the first constant term go away because they all have a factor of 0 in them, and we get the derivative evaluated at a is equal to c1, or c1 is f prime of a. Doing the same thing with the second derivative, we find that the second derivative evaluated at a is 2 times c2, and so c2 is the second derivative evaluated at a divided by 2. Let's make a little room. Okay, why don't you do the same thing with the third and fourth derivatives and see if you can find c3 and c4. So pause the video, take a moment, and when you're ready, start it back up and we'll do it together. And after you take the third derivative and evaluate it at a, you get that f triple prime of a is 3 times 2 times c3. So c3 is f triple prime of a divided by 3 times 2. And 3 times 2 is 3 factorial. You can think of it as 3 times 2 times 1. Similarly, you take the fourth derivative and you get the fourth derivative evaluated at a is 4 factorial, 4 times 3 times 2 times 1 times c4. So c4 is the fourth derivative evaluated at a over 4 factorial. And just by observing the pattern that we have happening here, we see that we've come up with an expression for the nth coefficient c sub n. It's the nth derivative evaluated at a all over n factorial. And here we're interpreting the 0th derivative as simply the function itself. And since we know the coefficients, we know the power series, what we call the Taylor series for the function f centered at x equals a, is f of x is the sum n equals 0 to infinity of each of these coefficients, the nth derivative evaluated at a over n factorial, times x minus a to the n, or f of a, which you can think of as the 0th derivative evaluated at a over 0 factorial, since 0 factorial is 1, plus f prime of a, which you can think of as f prime of a over 1 factorial, times x minus a, plus the second derivative evaluated at a over 2 or 2 factorial, which are the same thing, times x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed, and on like that forever. And just a quick note before we move on, the Maclaurin series that we came up with in our last video is exactly the Taylor series with a equal to 0. Okay, let's do an example. We had trouble coming up with a power series for the natural log of x because we couldn't find one centered at 0 because the natural log of x is not defined at 0. So let's see if we can find a power series for the natural log of x centered at 1. All we really need to do is find the coefficients of the power series, and we have an expression for the coefficients of the power series. Each c sub n is the nth derivative evaluated at 1 over n factorial, and so we just need the function and a bunch of its derivatives, and then we'll see if we can find a pattern. And here I've given the function and its first 5 derivatives. The derivative of the natural log of x is 1 over x. It's useful to write that as x to the negative 1 because it makes it easier to take the second derivative, negative x to the negative 2, and then it's easy to take that derivative, you bring down the negative 2, and you get a positive 2, x to the negative 3, etc. And you can see that, although I easily could, I'm not multiplying 3 times 2 in the fourth derivative or 4 times 3 times 2 in the fifth derivative, because it will be easier to look at those as factorials eventually when that becomes clear. And now I need to take each of these derivatives and evaluate it at x equals 1. And f of 1 is the natural log of 1, which is 0. It's easy to see that f prime of 1 is equal to 1, and that f double prime of 1 is equal to negative 1. We get that f triple prime of 1 is 2. 2 times 1 to the negative 3 is 2 over 1 cubed, which is just 2. And the fourth derivative, negative 3 times 2 is negative 3 factorial. So this is negative 3 factorial over 1 to the fourth, which is just negative 3 factorial. And the fifth derivative is 4 factorial. And you can start to see a pattern, especially when you look at 2 as 2 factorial and negative 1 as negative 1 factorial and 1 as 0 factorial. And recalling that the Taylor series centered at 1 for the natural log of x is given by this expression right here. We get the natural log of x is 0, which is the function evaluated at 1, that's the 0 right here, plus 1, which is the first derivative over 1 factorial times x minus 1. And then we have the minus 1 over 2 factorial times x minus 1 squared. And then the next term, the 2 over 3 factorial times x minus 1 cubed. And then we've got our negative 3 factorial over 4 factorial times x minus 1 to the fourth. And 4 factorial over 5 factorial times x minus 1 to the fifth. And it goes on and on like that forever. And we can simplify that a little. Notice that 2 over 3 factorial is 2 over 3 times 2. And the 2's cancel, and that just gets you x minus 1 cubed over 3. And similarly, 3 factorial over 4 factorial is just a fourth, and that gets us this term. And 4 factorial over 5 factorial is a fifth, which gives us this term, etc. And now it's very easy to see the pattern, which lets us write the natural log of x, or the power series for the natural log of x, in summation notation. It's alternating, and the first term is positive. That's why we need this negative 1 to the n plus 1. When n is equal to 1, 1 plus 1 is 2, negative 1 squared is positive. And then we've just got x minus 1 to the n over n. Notice that we can start at n equals 1, because when n equals 0, well, the first term is 0, and so we can just leave that one out. And the beauty of being able to write the power series for the natural log of x in summation notation like this is because, well, once you have a power series, the first thing you want to know about it is, where does it converge? And making a little bit of room. As usual, to determine where a power series converges, we use the ratio test. We look at the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. And here we have the usual simplification. X minus 1 to the n plus 1 is x minus 1 to the n times x minus 1, and the x minus 1 to the n's cancel. And then we can pull out the absolute value of x minus 1, because as far as n is concerned, that's a constant. And after observing that the limit as n goes to infinity of n over n plus 1 is just equal to 1, we get the answer, or the result of this limit, is just the absolute value of x minus 1. And so by the ratio test, we see that this power series converges whenever the absolute value of x minus 1 is less than 1. And the absolute value of x minus 1 is less than 1 whenever x minus 1 is between negative 1 and 1. And adding 1 to all the sides of that inequality gives us that that happens when 0 is less than x is less than 2. The ratio test further tells us that the power series diverges if x is greater than 2 or less than 0, but it doesn't tell us what happens at 0 or at 2. And if we look at what happens at x equals 0, well, plugging in x equals 0, we get 0 minus 1 is negative 1 to the n, so we have negative 1 to the n plus 1 times negative 1 to the n all over n. And regardless of what value n has, one of negative 1 to the n plus 1 and negative 1 to the n is negative, and the other one is positive, and a negative times a positive is a negative, and so we always come up with negative 1 in the numerator. And so this just becomes the sum, n equals 1 to infinity, of negative 1 over n, which is negative 1 times the harmonic series, and so that diverges. On the other hand, when we plug in x equals 2, 2 minus 1 is 1, and 1 to the n is just 1, and so we get negative 1 to the n plus 1 times 1 over n, or just negative 1 to the n plus 1 over n. And that's the alternating harmonic series, and that converges. And so we have that this power series converges for all values of x between 0 and 2, excluding 0, including 2. And just as an interesting aside, the fact that this power series converges at x equals 2 means that the series sum n equals 1 to infinity of negative 1 to the n plus 1 over n, which is the alternating harmonic series, well, we knew it converged, but now we know what it converges to. It's precisely equal to the natural log of 2. Okay, let's do this somewhat interesting example. We'll find the Maclaurin series, which is just the Taylor series centered at 0, for the function f of x equals x cubed plus 5x plus 1. And the first step is to take the function's derivatives. The function is x cubed plus 5x plus 1, so its derivative is 3x squared plus 5. Its second derivative is 6x, its third derivative is 6, and the derivative of 6 is 0, and the derivative of 0 is 0, and all subsequent derivatives also 0. And then the next step is to compute all of these derivatives evaluated at 0, which I've done here. And recalling the general form for the Maclaurin series for any function f, we have that f of x is equal to f of 0 plus f prime of 0 times x, plus the second derivative evaluated at 0 over 2, which is 2 factorial times x squared, plus f triple prime of 0 over 3 factorial times x cubed, and on like that forever. We get that our function x cubed plus 5x plus 1 is equal to 1 plus 5x plus 0 over 2 times x squared plus 6 over 3 factorial times x cubed plus 0 over 4 factorial times x to the fourth, etc., all the remaining terms having a 0 in the numerator. And when you simplify that, since 3 factorial is equal to 6, 6 over 3 factorial is just 1, it simplifies to 1 plus 5x plus x cubed plus 0 plus 0 plus 0 plus 0 forever. And so, not so surprising that x cubed plus 5x plus 1 is equal to 1 plus 5x plus x cubed. 1 plus 5x plus x cubed is the Maclaurin series for this polynomial. Okay, but now let's do something slightly more interesting. Let's find the Taylor series centered at x equals 2 for the same polynomial. So you take a few minutes, pause the video, give it a try, and when you're ready, start it back up and we'll see how you did. Well, the function hasn't changed, and so neither have its derivatives, so all of this stays the same. But now, instead of evaluating the function and its derivatives at 0, we're evaluating the function and its derivatives at 2. And we get these results here. And recalling the general formula for a Taylor series evaluated at 2, we get this expression here for x cubed plus 5x plus 1. It's f of 2, which is 19, plus f prime of 2, which is 17, times x minus 2, plus f double prime of 2, which is 12, over 2 factorial, or 2, times x minus 2 squared, and then 6, which is f triple prime of 2 over 3 factorial, times x minus 2 cubed, 0 over 4 factorial, times x minus 2 to the 4th, and then each of the following terms all has a 0 factor, and so they all go away, just like the fourth one did there. And simplifying the coefficients a little bit, 12 over 2 is 6, and 6 over 3 factorial is 1, and so we get this expression, x cubed plus 5x plus 1 is 19 plus 17 times x minus 2 plus 6 times x minus 2 squared plus x minus 2 cubed. And that's the Taylor series for this polynomial centered at x equals 2. You wouldn't want to keep going and simplify further. I mean, you could distribute the 17 times the x minus 2, you could cube the x minus 2 and the x minus 2 cubed term, etc. And you can simplify all this out, and when you're done, you'll get x cubed plus 5x plus 1, which might be a nice way to check your work, but this is what you want to leave to show that you know and understand how to compute a Taylor series. And you say to yourself, Self, why would I take a nice simple polynomial doing a fairly large amount of work and come up with a far more complicated and less simple polynomial that is equal to the one that I started with? And the only really reasonable answer is that in reality you wouldn't, but in practice it turns out that this is a pretty good Taylor series question. It's a gift. If I gave you a question like this on a quiz or an exam, this lets you show that you know how to compute Taylor series for a function that is very easy to take its derivatives, and there's nothing complicated about it. And so in any case, finding the Taylor series for a polynomial, good practice at finding Taylor series, even if it might not be the most useful Taylor series that you come up with. Should you actually get a question like this on a quiz or an exam, then you say a quick thank you and you work out the Taylor series. It's nice because the derivatives are so easy. Okay, those were Taylor series. Hope you enjoyed them. There is, of course, a homework on it. Hope you enjoy that as well. And I look forward to discussing them with you in class very soon.